Okay, so thank you for attending the session. So my name is Ejector. I work with the Autodesk simulation team covering Northern Europe, including Scandics, UK and Ireland. And what I intend to go through today is a little bit about Autodesk acquisitions, the challenges and product development process. Be looking at Moldflow Solutions, CAD/CAM solutions. Along the way we'll be looking at success stories, how the solutions have been applied, and summary at the end, and then I will take questions. So Autodesk have been investing in simulation technologies since 2008. Autodesk is determined to be the industry leader in design, simulation and automation for advanced materials and manufacturing processes. Such acquisitions have included technologies to allow us to perform CFD analysis, mechanical, plastic simulation, lattice and topological designs, 3D printing, additive manufacturing. So this gives us a nice portfolio to give us expertise in such areas of advanced polymers, short and long fiber composite materials, adaptive machining, in-process inspection, industrial additive manufacturing and hybrid additive subtractive processes. And all of these tools are not dependent on any particular CAD system, so they can add value for any customer wanting to innovate in materials and production. And two of the acquisitions, key acquisitions for looking at mold tooling, the injection molding process, is that of Moldflow. So Moldflow was established in 1977. It's a key brand name in the injection molding simulation world. And we also have Delcam, is one of the world's leading supplier of advanced CAD/CAM software for the manufacturing industry. They were also founded in 1977 after initial development work at Cambridge University, and they've been growing ever since. So high volume production can take the form of injection molding for plastics. It's a very competitive area, and there's a lot of pressure on pricing, which can squeeze margins from any project. So it's a differentiation into higher value business to address the needs of complex and more accurate tooling, helps to regain a competitive advantage through use of new technologies and increased machine utilization. And this is becoming more important as for the mold industry as designs become more complex and critical mold tool design questions need to be answered early in the manufacturing process before they become expensive. So if we look at the process of getting into injection molding, it is a complex manufacturing process. So in practice this could lead to high scrap rates if you're not producing parts to the desired quality. You may be running over cycle, your timelines on production could extend. Making molds is complex. There could be many iterations on producing your molds, getting the molds right, and that adds to the cost. And also we want the final part to perform, to be of the required quality, and to perform in service as well. And if they fail, if they're rejected, then it can involve rework, redesign. It's going to delay the manufacturing process, getting parts to your customers. So if we look at the design optimization process, typically we would see this process of validation. So going from design into manufacture, the costs will increase, and the cost of making changes as you go through from design, engineering, prototyping and production to make changes later on is much more expensive. It increases tenfold at each step as rework becomes more complicated, more difficult to do on existing designs. If we look at the optimization process, then this starts in the design phase, where we can start to optimize part design, mold design, and any changes at this stage are relatively inexpensive, and this helps to keep costs low during the process. So there is no need to validate. Once you get into production, you already know what to expect. You know that things will work first time. So information can be passed on from design, engineering, prototyping, and manufacture. So this means less changes are required. We can identify issues very early on. They can be eliminated at that stage, and there's no need to make major changes downstream. So it is a multi-stage development process. We look at the objectives of what we're trying to do at the top and the risks at the bottom. On part design, we want it to be suitable, to be fit. There may be structural requirements, but can we actually make the part? Will it be to the correct size? Once you get into mold design, there's tooling features we can do, such as cavity core design, cooling, ejection, gate and runners. But how do we know that the cooling design is optimized? It's going to give you uniform mold temperature. Is the feed system design going to give issues? Where should you vent the tool? Once you start cutting the mold, you can define tool paths. But are these optimized tool paths? Are they going to give you the risk of interference? Once you go into production, your molding parts, how do you know the mold will perform? And will the parts be accepted? Will they be of the desired quality? So we can look at this another way. We can look at the stages that we typically go through. And if we find defects while we're building the mold or while we're in production, then it goes back for rework, often involving redesign. It may be that the part has to be redesigned. So this is the typical process that we see. And as I said before, the costs do increase during this process. If we start to introduce inspection, advanced techniques for making the molds, then we can start to identify defects in the mold that could lead to poor parts being produced very early on. And then we can actually redesign at this stage and rebuild the mold. So this is area what we call forensic analysis, where before we go into production, we can do some inspection, some forensic analysis. And this can save us time compared to finding out these problems when we're in production or trying to get the mold into production. We can introduce CAE, simulation for plastics, coupled with mold design using advanced tools. We can start to identify any issues before the mold is built and eliminate them. So we can validate that the mold will perform before it is built, and this saves further time and costs. If we can start applying these technologies very early on, even at the design concept stage, information can be passed along, verifying wall thickness, material selection, injection points, etc. And this will further reduce the costs and time. And now we're actually optimizing as well. So we're not just checking that the parts can be made to the desired quality. We're not troubleshooting, we're optimizing, so we can reduce costs in this way by making the whole process more efficient, making sure we're selecting the right materials, and even reducing material content. So this has benefits for lower costs, reducing time to market, especially with warranty issues, recalls, and it gives you confidence that the design will be right. So Autodesk can deliver these solutions to help you. So it's a single source for parts, mold and injection molding process optimization. And it's using the leading plastic injection molding simulation with Moldflow and the leading machining technology with solutions from Delcam. So we'll begin with looking at Moldflow. So at the part design stage, you could be faced with these challenges as a part designer. Will the part fill without defects? Where should it be injected to make sure that it feels okay? Will it have surface defects? How do I know that I've chosen the right material for this molding? Will there be weld lines? Could be an area of weakness or visibly unwelcome. Will the part distort after it's been molded? Will it be to size and shape? And will it perform in service? Will there be any issues because of perhaps high internal stresses? And at the tool making, the tool design stage, there's lots of questions. So if you're adding cooling systems, are they in the right place? Are they optimized? And what mold shrinkages should be applied to the mold? Is the feed system optimized? Is it over-designed? Is it balanced? And what machine can it run on? What clamp force will be required? Will it be easy to mold? What will the cycle time be? Can that be reduced? If you've got other production tools, can they be reused again? We want to know the mold's going to run first time. We don't really want the production guy to be trying to troubleshoot any issues to try and get the part in production. So if we start with some of the basics, one of the issues, the main issues of poor product quality can be that of unbalanced flow in the cavity. So this means that some areas are filling before others, and while they're still filling other areas, these areas can become overpacked. They will shrink less. Lower shrinkage will mean different dimensions, and also it can induce warpage in the component. It can also increase clamp force, and the mold may actually open and flash. And we still see people sitting by machines trimming off flash. And this isn't always due to mold wear. It can be because of this unbalance where the mold is open locally to let material out. So Moldflow can help answer some of the basic questions of where to inject. If you've got this component here, we allow one injection point. Where would it go? There's recesses to the right. There's a lot of material to the left. Will it go in the middle, to the right, or to the left? And Moldflow can show you the best place to inject for flow. Simply going from blue to red, where blue is the best and red is the worst place. And in this case, we're leaning towards the right for the injection point. If you put an injection point here, we can actually see how it fills. So we're looking at contours of filling in time, and we can see that the ends of the component are being reached at the same time. And it says benefits for minimizing stresses in the component. It will reduce shrinkage variation. It keeps shrinkage under control. It can eliminate part warpage. It keeps clamp force to a minimum. And in turn, that can help with mold life. With the feed system design, the same principles apply here. Is it balanced? Is it going to deliver material into the cavity so that it fills uniformly? And the software is capable of resizing runners automatically to make sure cavities fill at the same time. It will allow you to look at the size of gates to make sure they're not over shearing the material, degrading it, or changing the colour of the material. So again, this can eliminate flash, reduce clamp force, and increase mould life. So one of our customers, Jaguar Land Rover, they had a 1+1 tool, and this gave problems during injection moulding. It's a poor balance between the cavities, and it resulted in inconsistent part quality. They couldn't get the sizes quite right for both of them. So they looked at resizing the runners, but it was difficult to achieve with the existing runner design. So the only balance that could be achieved was with like an S-shaped runner, so it actually gave a longer length to balance on, and that was very successful, and that gave them some savings just on that one tool. We go to another level. This is from Vistian. They partner with many companies for the design and manufacture of components. Looking at the instrument panel here, and initially this is going to be 2 moulds. One mould for a demister component and the main panel. And Moldflow showed that it could be moulded in one piece, in one mould. It would mean a witness mark from a valve gate being visible, but that was accepted because that could be covered by a hinged tray feature. So with Moldflow, they were able to establish best injection positions and feed system design with hot runners being used in this case, making sure that the fill was nicely balanced. You can see the fill pattern here. So this was very successful. Weld lines were moved to less critical regions by placement of the gates. Wall thickness variation will do that as well. Moldflow can also look at the details of hot runners. So detailed modelling of these can be achieved. And this helps you to see where the heat from such hot runner systems will go. Will actually get to the cavities, making them longer to cool, make them hotter on one side. And are they insulated correctly? So Moldflow will show the heat dissipation and allow you to make sure that your hot runner won't have any adverse effects on the process. Our customers are using Moldflow in various ways. Aljahmeir, they're a company that make large volume moulds. In this case, got a big recycling container. But they're using Moldflow to actually reduce the weight of the mould. So a lot of the weight's often in the fixed half. And by making sure they have the right injection positions, they can keep injection pressures low, stresses low, and they're able to redesign their moulds not to have so much material. They can reduce clamp force in this way, so the stress on the mould is not so significant. And this also has benefits for reducing the energy of the injection moulding machine. There's also mould cooling to consider. How is the mould being cooled? You need to take heat away from the hot plastic coming in. So Moldflow can show you where to best position cooling lines, shows you the effect of cooling line position on removing heat. This can be steady state or transient. You can interrogate results through the mould blocks, look at the effect of different mould block materials, see how many cycles are required to get the mould to a steady temperature, and look at the temperature variation within each cycle. cooling lines can be imported or added within the system. And this is an area that's often neglected because if you have differences on mould temperature from one side to the other, that can promote bowing of the component. It can affect final size. So one such company, Cooper Vision, they're already running a high cycle mould, high cycling mould. They're running at 11.2 seconds. They wanted to get this down to 8 seconds. This would have a significant effect on output. So using Moldflow, they were able to pay attention to the mould cooling, and they got cycle time down to 8 seconds. These molds run for 24 hours, 7 days a week for 3 years. So the quality has to be good, making sure that the modified cooling doesn't adversely affect the components in terms of size and the way it fills. Certainly we don't want to be seeing moulds being used as cooling jigs. So often parts can be kept in the mould for a bit longer to try and keep them to shape. But invariably the stresses will relieve themselves and you still end up with a warp moulding. So this twisted bin lid was kept in the mould for an extra 40 seconds to help keep it flat. So it's running over cycle time. They're making more bins and lids. It was center gated, and Moldflow showed that had it been end gated, it would be nice and flat. So rather than use the mold to try and eliminate warpage issues, Moldflow will show the cause of the warpage and allow you to eliminate it, preferably at the design stage, by paying attention to wall thickness variation, gate position, and processing conditions. Okay, now we start to look at the manufacture of the mold, and there's many challenges here. So there's the challenge of how do we actually make a large or complex mold. It won't be easy. How do we prepare for this? Can we read and surface solid wireframe and mesh from any CAD system? How can we eliminate errors that can cost us? You've got multi-axis machines. How can we improve the efficiency of these? There's always pressures to improve the surface quality and accuracy of molds. And are you finding that inspection is a cost or a bottleneck in your company? You may have different systems for making molds, for measuring molds, but are your operators trained to use all the different systems in-house? And are the suppliers keeping you up to date? And are you able to run lights out operations, mold manufacture and inspection with confidence? You may have invested heavily in quality control, but is that investment being effectively used? So there are CAD/CAM solutions that we can turn to. This is Powershape. So this is creating molds and dies and modeling for manufacture. This is where it excels. It allows you to create complex 3D geometry that you need to control your multi-axis or high-speed machine tools. It operates on 3D data regardless of which system created it. And it doesn't matter which format it is in. It can be solids, surfaces, wireframes, and even meshes. Once imported, intelligent analysis tools automatically detect and repair critical faults that could complicate downstream processes. And unlike many CAD systems, Powershape doesn't insist on you having to fully repair your solid before you can do further work. There's many commands, including direct modeling tools, which will still work even on faulty solids. So when creating cavities and cores and slides from a 3D part, Powershape will guide you through an easy-to-use wizard. In most cases, the shutouts and split faces are created fully automatically, leaving you minimum work to do to finish the mold. Powershape also contains dedicated tools to assist in the design and manufacture of electrodes for electrical discharge machining, EDM, which guides you through the entire process from design through to machining and even to driving the EDM hardware. You can take data from the electrode straight into the system without you having to manually enter. We're taking a text file, and this can eliminate any errors. So Powershape can import, analyze, fix and prepare complex models for manufacture. Also have Powermill. So many of the world's successful manufacturers grow their business by making increasingly complex parts faster and more accurate than their competitors. So to help achieve this, they invest in more modern capable machine tools, such as high-speed multi-axis machine tools capable of milling and turning, are able to cut complex parts in only 1 or 2 setups. However, the full potential of these machine tools cannot be realized without equally advanced CAM software. So this is where Powermill comes in. It has the flexibility to work on solids, surfaces, wireframes and STL meshes imported from any CAD system. It contains a comprehensive selection of 5-axis toolpath strategies, each able to drive a wide variety of tools, including specialized cutters such as lollipop and barrel tools. And with Powermill, your tools are machined how you want to machine it rather than how your CAM software wants to machine it. It excels at two-path optimization, and they can be trimmed and reordered to suit your needs. For good surface finish, Powermill allows you to modify entry and exit mills, cut directions, and many other machining attributes, all without costly and time-consuming recalculation. You can create your own toolpath macros and templates, which allows you to fully automate time-consuming repetitive tasks. Programming time can be reduced by taking advantage of 64-bit multi-core PCs that people use today. PowerInspect is 3D measurement and metrology software for a wide range of measurement hardware across all your inspection hardware. It makes inspecting complex free-form surfaces very simple. So programming must be easy, measurement should be quick, and reports should be easy to understand. Sequences can be created ahead of time to maximize machine utilization and save time in the reporting. Simulation, collision detection, and avoidance allows you to be confident that sequences will run successfully. So if you're using a variety of measuring systems, many companies have this. This can include coordinate measuring machines. They provide accuracy. Things like arms, laser trackers, optical systems, and scanners allow you to measure in situ. There's machine tool probing, which allows you to measure during the manufacturing process. So you may have different systems for measuring, but are all your operators using the equipment effectively? So PowerInspect provides a single platform allowing you to manage all the measurement in a single process, which provides flexibility and allows you to balance the workloads. So we have some customers. There are many customers. I haven't got all the time to go through all of them, but one such company is WHS Plastics. They're a tool maker for automotive. They do injection molding. They have 100 injection molding machines. They have machine tools, spark eroders. They operate over 2 sites. So they have products such as Powermill, Powershape for their tooling strategies. And this allows them to directly address time to market. They do collision checking and simulation, so they can run at full speed, lights out, and this helps also to address the time to market while controlling the quality. And this company achieved a 20% greater throughput from the existing machines in the first 3 months of use. There's many other companies, so Mould Solutions in Ireland. They make precision moulds, mainly for the medical industry. They perform injection moulding, based in Ireland. They also have, apart from having products such as Powershape, Power Inspect, they also use Moldflow to optimize the mould design, the part design, before mould construction takes place. Town Light Engineering, also in Ireland. They also make for precision moulds for the medical industry and also perform injection moulding. Go Tools, precision tool makers, based in Yorkshire. They make moulds for automotive, medical, consumer, electronics and packaging. Some examples there. So what else do we have that can help with tooling? Well, if we look at the traditional way of cooling moulds with simply straight drillings, water lines, we're now considering, many companies are considering using conformal cooling. So these can be cooling channels, cooling blocks that follow the contours of the part, give you more uniform and efficient cooling. So if we take this blender, for example, we can use Moldflow to simulate how the component will feel, make sure that there's no adverse effects on part quality. Moldflow can also perform conformal cooling analysis. So it can look how the cooling lines perform. So in this case, these aren't simple drillings, these are more complex cooling lines designed to remove heat from the component effectively, inside and out. And Moldflow can predict the temperature of the plastic, the temperature distribution required to have heat removed. So it works out the heat load that the cooling lines have to work with. We can also use the pressures inside the cooling lines and the pressures inside the cavity from the injection moulding process to look at the stresses in a conventional mould. Which area is actually absorbing the stress? We can then go on to perform an analysis where we can come up with a new structure. So in this case, we've seen a lattice structure which is designed to absorb those stresses, absorb those forces from the cooling lines and the injection melt. So this offers a great reduction in mould volume and mould weight. So we end up with a lattice structure. This cannot be made by normal means. This would have to be made by such processes as additive manufacturing. We can then build the bolster around this. So we can go from initial simulation of conformal cooling, identify where these cooling lines should be, design a mould to support this, evaluate the stresses and loads in the system, further redesign the mould to be supported. We end up with a mould that can be 45% reduced in volume in the conventional mould, and also offers a 10% reduction in cycle time. So that mould will have to be made by additive manufacturing, and this is another area where Autodesk can excel and are leading and simulating. So a lot of structures, a lot of components can be made by additive manufacturing, 3D printing, whether they're plastics or metals. But this process does not come without its own issues. So your heating metal, you're melting it, it's cooling down, and this can give rise to thermal stresses which can cause cracking. Also, you need to support such structures while you're building them, and the supports can also fail. So with such products from within and NetFab from Autodesk, you can help to optimize this process. So it can simulate how the build is performed, temperature distributions, stresses, and also can predict deflection or displacement of the final product. Will it be to the size you want due to distortion, due to thermal stresses? So it's best to know this up front, because such processes can take many hours or days to complete. We're also looking at Moldflow ejection force, which is in development at the moment. So this will use our embedded Nastran solvers in our structural analysis programs, and it can look at the ejection forces required to remove a component, and also to help you place your ejector pins and also size them without perhaps giving these visible stress marks that we often see on components, which can be distorted, can be stressed during the ejection process. We're also looking at predicting mould life. So if you consider that a mould goes through a lot of stress cycling, it's got hot plastic coming in, which is then cooled. It's got high pressure melt coming in, and that pressure dissipates. And you've got mould clamping forces around the mould. These can all induce stresses in the mould. And using a fatigue analysis, again from our Nastran solver, we can predict fatigue, we can predict mould life, identify which parts of the mould will fail first, and also identify what is the cause of this failure. Is it thermal, is it pressure, or is it clamping force induced stresses? Okay, so I'd just like to summarize, put some things together, summarize what we have seen today. So we're looking at complex tooling. We need to get costs down to be competitive, so we need to be more efficient, and parts are becoming more complex. We need to make critical decisions very early on. So we can use the combination of Moldflow and the CAD/CAM solutions to help drive this. So we can begin with Moldflow to evaluate best gate positions. The part can be filled defect-free. Will there be weld lines, air traps? Can we eliminate distortion? We can look at conventional injection molding, two-shot, insert over molding, other processes as well. But we need to make sure the part is manufacturable at this stage. Once tool design is completed and ready for manufacture, focus turns to improving quality, accuracy and repeatability and finish of the machining process. High efficiency tool paths, both in terms of calculation and cut time, are important to minimize project lead times. Minimizing tool lengths to reduce vibration and improve surface finish can be achieved by using the full capability of multi-axis machines. Tool axis decisions can be made prior to calculation or quickly applied afterwards, fine-tuning the output desired for the machine. Simulation and verification before machining can reduce downtime, providing confidence for unattended production. Taking a right first-time approach means making sure the material is loaded in the right position prior to machining. Automated part alignment means a quicker, accurate and consistent setup. Part of verification while the component is still on the machine can be used to check the accuracy. For finer details, electrodes can be used to finish areas of the tool that cannot be machined by conventional means. Electrodes can be extracted directly from the model, machined and inspected, as well as being positioned accurately in the EDM machine itself, all with an automated workflow. So what we've seen Powershape for mold tool creation, Moldflow for molding simulation and analysis, Powermill for toolpath creation and machining, and PowerInspect for inspection. Also looked at the electrode. This combines Powershape, Powermill and PowerInspect to provide a closed-loop system between electrode design, manufacture and metrology. And all of this to deliver high-value tooling. So Moldflow to answer critical mold tool design questions before they become expensive. Evaluate different design possibilities before the mold is built. Looking at products like Powershape for optimum tool path creation without recalculation. Preparing your models for manufacture. Products, solutions like Powermill, making sure we've got collision-free tool paths, making sure we can run unattended production with confidence, and evaluate optimized setups for different machines that you may have on your premises. Okay, so the takeaway that we have for you is that Autodesk Solutions provide the capabilities to thrive in the future of making things. So it helps you to keep pace with the way things are being manufactured. We need to be more efficient, parts becoming more complex, and using the solutions that I've been showing today, this gives you that ability. And the bottom line is for you to win higher value business in the tooling industry using the unique breadth of solutions from a single vendor. Okay, so I'm at the point where I can take questions. I've hope you have found that very useful.